Scott Mitchell from Stud.io. He is the founder and CEO of Stud.io, a computational construction company. Before founding Stud.io, by the way, I need to ask Scott what I.O. means, and I'm sure you explain that, No? Okay. Before founding Stud.io, Scott worked as a full-stack software engineer at Autodesk as part of an AEC generative design group. While working at Autodesk, Scott has access to a Howick roll-forming machine, which he experimented on in his free time before ultimately leaving to focus on that interest full-time. As a student, Scott studied film, music, architecture, and computer science. In other words, making things. He still enjoys composing for the guitar, producing videos and animations, and experimenting with software development and fabrication research at the Autodesk Technology Center, where he is a resident. In the past several years, Scott and his wife and their golden retriever, Lou, love it, have lived a somewhat nomadic lifestyle, traveling to and living in various cities across the United States, including Boston, Massachusetts, Los Angeles, Austin, Texas, Tulsa, Oklahoma. They now have a 6-month-old now. That was 2 months ago when this was written. 6-month-old son, James, and are based out of Boston, but probably going to move soon. Yeah, but I'll let you tell everyone about that. I'll give you Scott Mitchell.
Thank you, Cindy. Thank you all for being here. Like Cindy told you all, I am Scott Mitchell, and I'm the founder of Stud.io. Our mission at Stud.io is to enable architects to build some of their boldest ideas. And a lot of times that means geometric complexity. And we enable that by inventing new parametric fabrication systems and then developing the software to automate the design and fabrication of those systems. So Cindy gave you a little bit of my background, but the story I'm going to tell starts with the Howick machine. So before founding Stud.io, I was a software developer at Autodesk. And before that, I was an intern at Autodesk for a summer. And they basically, day one, showed me the Howick machine. And they said, we just want you to spend your summer seeing if you can do anything cool with this machine, which was an awesome project prompt. But at first glance, I was like, this machine just does one thing, right? It just makes studs and punches holes in it. And it looks like people have pretty much figured out everything you can do with that machine. And for those unfamiliar with the Howick machine, it rolls up steel studs and tracks, and it punches holes at some point along the length of it and then cuts it to length. And the machine I was working with did these 8 punches right here. But after diving into it for a couple of weeks, I started to realize that you can create some complexity and things people hadn't thought of before based on the simple, basic operations that the machine is capable of. And this right here is really foundational to how Stud.io operates, how it designs things, and how it develops software. So CNC machines have basic operations they're capable of. We develop software that understands constraints around connections that apply operations to members. And these connections get aggregated into versatile systems that you'll see a couple examples of here in a second. So let's look at connections first. This one's a pretty useful connection. We call it the handshake connection. It's basically 2 studs back to back. And if you take that 3 web hole punch on each one and overlap one of them, and then do that again on the other side, put a screw through those alignment holes, you fix 2 studs at some particular angle, whatever angle that is that you want it to be. And also notice that connections have constraints. So 2 studs that are back to back, the constraint is that they have to be facing in opposite directions. So the software determines the orientation of members and then applies operations to those members to make that connection exactly how you want it, 111 degrees or whatever, once you get it out of the machine. So then if we look at combining connections into systems, so this is a pretty typical connection. You get 3 members, stud to stud, dimple connection that's flat though. But if you bring in the handshake connection into the structure as well, you can start to break out of the plane into complex geometry. And as you expand that in a series of multiple different connection types, you can start to do really interesting things. And so this is actually one of the first systems we developed. It's a reciprocal structure. We saw an early version of that a second ago. But the idea here is that ultimately you can feed in any surface you want, any complex surface, whatever, into the software, and it tessellates this pattern across the surface, and you have all of the unique members that you need to go build it. All the holes are in exactly the right places. Basically just use the Howick machine to create your Lego set and go put it together, and it matches your surface perfectly. And it works. We've built a few of these things, basically just trying to do interesting geometry. This was an installation we did at AU a few years ago. This is another one. What's really interesting about this one, it was at a party. The bar was inside of what we call the Space Igloo, which we thought was pretty cool. We showed up the day of the party, created our files, created our parts on the machine with those files, and built the thing before 5 o'clock when the party started. So getting back to this, you've seen how the simple operations that the machine is capable of applying very precisely can generate complexity if they're combined in the right way. And this is really where a lot of the creativity happens. And it reminds me of other things that I've done in my life, like games or like chess. It's almost like the operations that the machine are capable of, which are really simple, like your pieces. So the pieces in chess aren't very interesting alone, but they have moves and constraints on those movements. And it's how you combine those moves to create strategy that's really interesting. And the same thing's true with music. Like your notes are sort of the atomic level of music, which have constraints, like Western classical music implies constraints for how you combine these notes into harmonies or into chords. And of course, you connect those in time to create compositions. It really feels the same way with what we've done with the Howick machine over the past few years. Basically starting with something simple and a system of rules and constraints, as well as an understanding of when you might want to break those rules to create really interesting stuff. So I think what's unique about Stud.io is that we play the Howick machine like a game. We play the Howick machine like you would play an instrument. And the reason that I feel that's valuable is because CNC and digital fabrication equipment is designed with some set of use cases in mind. And then people develop off-the-shelf software to support the process of using machines in some way. But really, I think that's just a small subset of a lot of latent potential in pretty much any CNC machine, and Howick machines in particular. And I think the reason that people aren't in that other vast space is it takes one, curiosity and playfulness and a willingness to experiment, and those experiments potentially fail. But also, your own design tools. We're developing software that helps you to move more feasibly, more quickly through that space and explore it. And so what we're doing is slowly expanding the capabilities of the machine. So there's like this boundary of what's feasible. And we do experiments all the time that don't have any immediate tangible value, but are just pushing that boundary outwards. And if they're not immediately valuable, they almost always are at some point down the road, either leading to another idea or it's an actual thing that we use on a project. So I think if you made a map of our capabilities and our software's capabilities currently with the Howick machine, it's this growing, amoebic, branching, just really interesting exploration into the space of potential of the machine. And one of my favorite examples of that is curved studs coming out of the machine. And the reason that's my favorite example is, to the best of my knowledge, the Howick machine wasn't designed with that feature in mind. Okay, that is correct. It just happens to be possible with the features that it was designed for. So it's meant to make straight studs. It happens if you use a couple of those operations in a unique way, you can start curving studs that come out of the machine. And the way that works, it comes out straight, but you're using this end truss punch that's typically at the end of a stud in the middle, as well as two dimples on the side of that. And if you snip one side of the end truss, overlap those holes and put a screw in it, this thing starts to fold up into a predetermined shape. So not just a circle or an arc, any sort of curve that you want to create with the stud, you can do it. It's just about where you place those holes. Some other experiments we've done. This one was before I founded Stud.io. for like a month. It was another party that we were looking to create some cool stuff for. It's usually an excuse to experiment. We wanted to build some cocktail tables. So for like a month, I'd get home from my day job and just like sketch and then use our software to design weird cocktail tables using the Howick machine. And I probably did like 30 or 40 of them, picked 10 of them and built them and had drinks on them, which is pretty cool. So I like that part of it. I think there's two reasons I really like this, and it's almost like one of the proudest projects I have, even though it's a small one. Like, first of all, like pretty sexy tables. And second, it's this library of connection details that we can pull from and still do pull from on real larger projects to this day. Another thing we did that definitely didn't have any immediate tangible value was we built this bird. And the reason that we did that is thought it would be cool, one. Two, we have this system we call a faceted surface system, usually for large architectural applications, but had a feeling that we could do highly articulate surfaces, like the geometry of an animal or something. Take that to a music festival or something like that. So just to prove that that was possible, we built this bird, went together pretty quickly. And some of the detail that I want you to notice, because this is still that architectural system, just trying to proving what's possible with it. So if you look at some of the detail of the faceted surface system, there's kind of this like interlocking frames at the chest plate there. You should see pretty much the same thing here. So this is the same system, but just applied architecturally. But we did this, usually the facets are way bigger. So we did this after the bird, after we kind of proved to ourselves, we can actually do super articulate types of geometry. And that was actually an interesting project for other reasons. So they wanted to be able to disassemble it and reassemble it at a number of different events. And one of the events, they had to take an elevator to the space that it was going to be displayed in. So each of these, we broke it up into 19 modules that had to fit into an elevator so they could be bolted together on site. And this thing actually goes together in like an hour, so not too bad. And then you can see the finished product on the right. I'm just going to quickly go through some other projects that we've done. This one was a museum in California. There were 193 unique panels. Here's a couple of them, but just super organic custom shapes. We developed a system that could generate their framing, as well as a whole bunch of other deliverables, including the GFRC molds that they got cast into. This was this crazy curvy surface, relatively small project, but probably the most complex thing that we've done, but ended up working out really well. And this is actually an earlier version of the faceted surface system I was talking about a minute ago, but just showing you guys what it looks like in an architectural application. So that's kind of the theory behind what we do. I want to, a couple minutes remaining, show you how we provide value on projects based on this history of playing around with digital fabrication equipment. So this is the Sphere in Las Vegas, and we were brought on to help with what's called the collar. So basically this ring around the bottom. Just a couple quick things to note about the geometry of the scope. It's obviously curved in plan. It's also sloping in elevation, so there's some engineering constraints around different height panels. And then most importantly, and we'll get into this in a second, like it is tilted in section. And that tilt is variable. So it's kind of tilting out, coming back. So that changes as you move across the collar. And we looked at a variety of different systems. The system that we ultimately ended up applying to the scope was an EFIS system, which has frame, sheathing, foam at a high level. Those are the components of it. The main thing to take away from this slide, though, is all the components of that system are flat. And we obviously didn't just look at flat geometry. So a big part of what we do is we come in and it's like, okay, based on all of the software and the capabilities we have, how are we going to build this? Let's start to explain it. Let's start with something simple. So a flat wall is pretty easy to make flat panels out of that. Even if you tilt that wall out, flat panels, rectangles, easy. You start to see issues when you go around a curve. So these things are, say issue number one is that they're fanning out in elevation. So you get this gap at the top, which is not good. To fix that, you just move your rectangles to become trapezoids, fill in that gap, we're good. Issue number two, remember that tilt wasn't constant. So if we want a variable tilt, let's say it's 80 degrees on the left, 60 degrees on the right, we see issue number 2, which is that these fan out in section as well. Which was not the design intent, so that's not good. And even on a straight wall, that's a problem because they're kind of incrementally leaning down. So what you want to do is you kind of want to like push a corner to its neighbor so that it's all lining up. The problem is it's obviously not flat anymore. But that does at least give you a controlled approach to panelize the surface. But we didn't stop there, so we continued our investigation and realized that the top and the bottom circle that are defining this thing also define a cone, or an oblique cone specifically. And what's good about a cone is it's basically a pyramid with a bunch of sides that are flat. So if we run our joints through the apex of that cone, we have flat panels. The downside is that our joints are running through the apex of that cone, not necessarily straight up and down. So it's basically this trade-off between flat panels, kind of weird joints, or do we want twisted panels and the original design intent joints. So we can really quickly run this stuff through our software, and these are kind of like prototypical panels, so not full scale, and ignore a couple other details, but we can evaluate and show the client what that looks like and what the system would be. So we have conical on the left. Obviously the joints look a little weird, but we can do it, and all those parts are flat off the shelf. Or we have twisted on the right, which is what we ended up going with. And what we did is we kept everything flat behind the foam, and the foam has a flat backside and a twisted front side. And it's among the deliverables, like files we can export from our software, includes CNC files for like a hot wire cutting. So we just move the complexity of the twist to the foam. So then looking at what that actually looks like applied to the project, developed a system, automated system for that specific project. And obviously you have the frame, you have the handshake connection to get a horizontal frame on the bottom so you get the right tilt. They also have alignment holes between this brake shape and between the frame on the bottom to get like this brake shape on the bottom that you use for layouts, like super precise layout onto these pins. Obviously you have the sheathing, and then you have the custom foam, which, like we said, is variable thickness, right? So those things have to be digitally fabricated and well controlled. But again, once that system is put into place, it uses our software inside of the Grasshopper visual programming. You just run the panels through it, and you guys don't need to see all of them. But at the click of a button, once you have that system applied to the project, it's just export various files, including files to the Howick machine, files to assemble the parts coming out of the Howick machine, stuff for the hot wire, stuff for layout, etc. So that's basically it. This video shows proof that this actually works. Basically just shows all the details I was just talking to you about. We've got the frame comes out. Frame drawings are automated as well. And they put these things together. You guys are probably familiar with most of this process, but I do think this is pretty unique that each panel had a different angle, right, that the frame has to tilt out at. So that handshake connection at the bottom gets you that, and it takes the people on site no time to put it together. And they don't have to get a protractor out or anything like that. It's just line up the holes and put a screw in it. And then that brake shape, again, it has alignment holes from the brake shape to the frame as well. Which I think is a tactic that we use all the time. The Howick machine produces such accurate frames. We can basically use it as a jig for other components. So we can include alignment holes or registration holes on the frame that other parts are registering to. And then one thing that we've gotten into recently is a digital install as well. So exporting files for, this is a Hilti total station, basically pinpoints exactly where those pins that were going into the bottom of the panel are supposed to be, and then also gives you points on the finish. So when they drop this thing into place, they can check to make sure it's in exactly the right place. There it is. This one's going up right now. But anyways, that's how we apply what we've learned to actual projects, and this is the kind of stuff we're doing now. So thank you all very much.